In this video, we're going to go ahead and look at the concept known as steady-state error. So recall from our performance analysis, if we have a unit step input into a system, we looked at, say, time versus the output of the system, and we looked at second-order systems that did something kind of like that, and they would finally go to some steady-state value. What we haven't really looked at is what if there's an offset or an error between the final value that we command and the final value that the system takes on. In other words, what is the error between the command, say R of t, and the output of the system, Y of t, as t goes to infinity? And this is what we would consider the steady state. So steady-state error can come from a number of sources. One could just be a DC gain, and we've looked at the idea of DC gain, and so there may be a difference because of the plant between the reference input and the actual output, and we can adjust that with a simple filter. As an example, consider the plant that's given by, say, k over s plus 1. And let's say I'm running open loop, and my input here is a step which is 1 over s, and I've got y of s over here. Notice this is stable, so we can use the final value theorem, and we see that the limit of y of t as t goes to infinity is equal to the limit of s times y of s as s goes to 0. But y of s is just the transfer function, say, call this g of s, times the input, 1 over s. So that's the limit of s times y of s, which is g of s over s plus 1, times the input, which is 1 over s, as s goes to 0. These s's cancel out, and I'm left with k. So this is our steady-state gain, and it also could show up as an error between what we want and what we're actually commanding. This is that idea of open loop. But what happens when we close the loop? When we close the loop, we can look at this question in two ways. We can look at the idea of a tracking error or a regulation error. We're going to start with tracking. So we're going to use a series compensator. So in this case, I have my input signal R of s, which is then feeding, after I generate an error, into my control loss, C of s, which then feeds into the plant, say g of s, and I measure an output y of s, and I take that measured output and feed it back with a minus sign. And we notice that E of s is just the reference minus the output, and if we make some substitutions, I get y of s is just g of s times C of s times E of s. And if I solve for E of s over R of s, I'm left with what we call the error transfer function, which is 1 over 1 plus C of s times G of s. This is known as the error transfer function. Now we can look at if the final value theorem applies, which we would need stability in our error transfer function, then we can say that the limit of the error in the time domain as t goes to infinity is equal to the limit of s times E of s as s goes to 0, which if I substitute in my steady-state error, I have the limit of s times 1 over 1 plus c times g times r as s goes to 0. Now, of course, the value of this limit is going to depend not only on C and on G, but also on R. So a lot of times we'll look at let R be a unit step or just 1 over S. And notice now that implies that this limit is just 1 over 1 plus CG as S goes to 0. So a lot of it here depends on the CG, which is also known as our loop transfer function. We can go ahead and do an example here. Let's let g of s be a simple system, 1 over s plus 1, and c of s, we'll just use a proportional controller, and we'll let that be kp. So now, in this case, I can write down that our steady state error, which is defined as the limit of s times the error transfer function, all as s goes to 0, is equal to the limit of s times 1 over 1 plus kp times 1 over s plus 1. And here we're going to let r of s be 1 over s, as s goes to 0. So those s's cancel out, and now we just have to look at what happens to the remainder of the transfer function. So this is equal to the limit as s goes to 0 of s plus 1 over s plus 1 plus kp. I let s go to 0, and I get 1 over 1 plus kp. Notice this does not equal 0 unless, what? Kp goes to infinity. So we can show how this works in MATLAB. One way to analyze the steady state error of this particular example problem is to use MATLAB and the step command. If we first define the transfer function g using the tf command, and then define the controller as just a unity gain, then we can actually use what we call the feedback command, where we give it the forward loop for the two different transfer functions, so c times g, and then unity feedback has a 1, and it assumes negative feedback. So there's our closed loop transfer function. Then finally we can use step t, and we get a plot, and we notice that the final value that we get to is 0.5, not 1. If we go ahead and change the value of kp in our controller, let's let it be 10 now, and then we use the same feedback command and the step command. Notice the final value, we get up to about 0.91, which is just 10 over 11. We see that down here in the transfer function. So as kp gets larger and larger, we're going to get closer and closer to the final commanded value, but we're never going to quite get there. This is an example of how steady state error can show up in a feedback system. Finally, we can look at the same kind of problem from the point of view of what we call regulation. Tracking was the idea that we wanted to track a reference input. Regulation is where we want to set the reference input to 0 and then keep the system regulating to some value in the face of a disturbance. So in this case, we have a reference input, which we're going to set to 0, and we feed that into our control law. And in this case now, we have a disturbance coming in, call it w of s, which is then the sum of that disturbance plus the controlled error, feeds into the plant, g of s, which produces an output, y of s, and that output is being fed back to the minus sign. So we still are generating an error here. This would be equivalent to, say, a spacecraft flying through space and having a constant drag term, or it could be gravity when it comes to doing the analysis of an aircraft. But either way, it's this constant term that we maybe, or it doesn't actually have to be constant, but it's some sort of disturbance entering the system. So what we want to know is once we let r of s equal 0, we want to know what is the steady state error. Well, I have to again solve for the error transfer function and have the same idea. The error is going to be the reference minus the input to the system, but the reference is just equal to 0, so this is just minus y of s. And if we go ahead and solve for the minus g of s times w of s plus c of s times e of s, and if we go ahead and now solve for e of s over w of s, we end up with minus g of s over 1 plus g of s times c of s. This is known as the error transfer function for regulation, and notice it looks very similar to the error transfer function for tracking, only instead of a 1 in the numerator we have g of s, and we have this minus sign. So this is going to be important when it comes to looking at what these steady state errors actually are. So again, we define the steady state error as the limit of e of t as t goes to infinity. And if the final value theorem applies, we can say that's the limit of s times e of s as s goes to 0. So again, we need a stable denominator here in this transfer function. Upon substitution, we have the limit of s times minus g of s over 1 plus g of s c of s times w of s as s goes to 0. So again, this steady state error is going to depend on the type of disturbance and the nature of the plant and the control law. Again, can look at the same kind of example that we had in the case for tracking, where we let the transfer function g of s be defined as 1 over s plus 1, and that the control law is just a proportional control gain. And in this case, we're going to do the same thing. We're going to let w of s equal the step input, or step function, 1 over s. So we go ahead and we notice that the system is stable. So we can calculate the steady state error as the limit of s times 1 over s plus 1, the minus sign, over 1 plus kp times 1 over s plus 1 times 1 over s as s goes to 0. Again, those s's cancel each other out, and we're left with the limit as s goes to 0 of minus 1 over s plus 1 over 1 plus kp over s plus 1. Multiply both numerator and denominator by s plus 1. We get the limit as s goes to 0 of minus 1 over s plus 1 plus kp. We take our limit, we actually end up with minus 1 over 1 plus kp. For rewriting, we end up with the steady state error is minus 1 over 1 plus kp. In this case, the steady state error in the regulation problem happens to be the same as the error in the tracking problem, only with a minus sign. So again, we can see this in MATLAB. Let's go ahead and look at the example for the regulation steady state error problem. If we go ahead and again define the transfer function as 1 over 1 over s plus 1, and we set our transfer function, our control law to 1, we can go ahead and calculate our steady state error by taking the minus g and dividing by 1 plus c times g. And we end up with this transfer function. Now notice that it looks second order, but if you look at it long enough, what you notice is that there's a common 0 and pole that will actually cancel each other out. So if we type step e, then when we look at the figure, we find that we start at 0 and the error goes to minus 5. Now if we were to change the gain on our controller, say to 10, and we again calculate e in the same way, we type step e, and we go ahead and look at the figure. Now what we see is that that steady state error is reduced to minus 0.09. So the gain that we choose obviously affects the final value of the steady state error as indicated by the analysis. In conclusion, what we notice is that the steady state error is impacted by this feedback loop that we put into the system. So while feedback is useful, it can also generate these errors that we're not expecting. And we need to understand how our control design, or our control law C of S, affects the steady state error, and what kinds of disturbances or reference inputs that we can track given that we want to send the steady state error off to 0.